be deriving kinematics equations of motion in one dimension, 1D motion. So we know that average velocity equals to change in position over change in time. So now that's the average velocity over time. So now if you want to find velocity at any instant, so in general we talk as velocity, so for that change in time has to go to 0. That means very small period of time. So we did this with respect to the speed. So speedometer in your car gives you speed at any instant. Okay, so now in terms of velocity, now we have to be careful with direction. Velocity is a vector quantity. You need both magnitude and direction. So velocity equals to limit change in time that goes to 0. Okay, then change in x over change in time, we can write that as derivative of position over time. So dx dt, velocity can be dx dt, which can be greater than 0, equals to 0, less than 0. Similarly, acceleration, which is change in velocity over change in time. So now that's the average acceleration. So if you want to find the instantaneous acceleration, we do the similar thing as we did that for velocity. Acceleration, limit of change in time goes to 0, change in v, change in t, we can write that as dv dt or d dt. Okay, since velocity is change in x over change in time, okay, we can write that as dx squared dt squared. Okay, or let me rewrite the whole thing. A equals to dv dt, which is dx squared dt squared. Okay, where this can be greater, acceleration can be greater than 0, equals to 0, or less than 0. All right, now using acceleration, okay, acceleration is dv dt. I'm going to change my ink color. Let's see, which one do I want to pick? Let's pick this. All right, so we can rewrite this equation as dv equals to acceleration. Why does it do this? I don't get it. dt. So let's say if an object goes from has initial velocity of v naught to the final velocity v. Okay, start time is 0, final time is t. Okay, v, if we integrate both sides, integral of dv is v. Okay, v naught v, integral of a dt is at. Okay, time. Okay, let me rephrase it. Let me redo this part. I forgot to mention something here. So since acceleration is constant, we in this class the maximum time dependent we'll do is to the second degree. So in that case the acceleration is going to be constant. So acceleration is constant. So A comes out, 0t dt dv v naught v. So now that becomes, taking the integral of dv v, so we get v minus v naught equals to at, which we can rewrite as v equals to v initial plus at. The final velocity is dependent on the initial velocity and acceleration and time. Okay. So v naught here is a constant. So I'm going to call this equation 1. All right, now taking v velocity, which is dx over dt. Okay. So I can rewrite this as dx equals to v dt. Why? I don't know why we get this happens here. So if I take an integral on both sides, let's do two different ways. One, when v is constant, so when v is constant, so dx minus x naught vt. Rearranging this, we get x equals to x naught plus vt. I'm gonna call this number 2, equation number 2 for now. Okay. So if velocity was not a constant, so dx equals to integral of v dt. If it was not a constant, so if you started from x initial to x dx, v was not a constant, we can replace that equation number 1 into this v, so that becomes v initial plus at, take integral with respect to dt, so this becomes x minus x initial, which is v naught dt. Forgot to write this time here, plus integral of 0 to t a t dt. So x minus x naught, this becomes v initial t plus 1/2 a t squared. Okay. I'm gonna call it number 3. All right, next. We know the equation for acceleration, which is dv dt. So now if we apply the chain rule, a derivative of v with respect to x, derivative of x with respect to t. If we have this, we get dv dx. Derivative of x with respect to t is v. If I rearrange this, I get a dx v dv. Okay. In this case, acceleration is a constant, so I'm going to pull it out, going from x, v initial to final velocity v. So we get a x minus x naught v square over 2 v naught. So this becomes 2a x minus x naught parentheses, so v square minus v naught square. So velocity final square equals to velocity initial square plus 2a in final position minus the initial position. So I'm going to call this number 4. So by definition, okay, or rewriting equation number 1, we get acceleration equals to v minus v initial divided by time. Okay, where time, when you rewrite that, time equals to v minus v initial divided by a. Or rewriting equation number 1, we can also say v initial equals to v minus at. Okay. So now if we substitute this a, okay, in equation number 3, so we have x minus x initial, which is equation number 3, v initial t plus 1/2 at squared. Okay. So if I replace that a in this equation, we get v initial t plus 1/2. A is v minus v initial divided by t times t squared, so t cancels out here. We get v initial t plus 1/2 vt minus 1/2 v initial t. Alright, so I have my daughter coming up, so she might interrupt me right now. 1/2 v plus v initial t. Okay, so that gives, we can rewrite this as x minus x naught divided by t equals to v plus v initial divided by 2 by, as we have learned, this is the average velocity by definition, t minus t. Sandy, do not disturb me, just a second. Okay, which is the average. Okay, so now if we take this average velocity, okay, I take acceleration as I have written in this part here, okay, and substitute that in this average velocity equation. I get x minus x naught. Now in this case I'm substituting this time, v minus v initial divided by a equals to v plus v initial divided by 2. Okay, rewriting this, okay, this becomes x minus x initial times a v minus v initial equals to v plus v initial divided by 2. Rewriting this, cross multiplication, 2 times x minus x initial a equals to, okay, so we go back and algebraically we have this equation. Okay, this was our equation number 4 again. So algebraically, using that average velocity formula and equation number 1, we found that. So now, okay, there's one more that I want to. Similarly, if I, okay, this one I'm missing here. So if we rewrite that average velocity formula, x minus x naught divided by t. Okay, let me change the color of the ink so that we know what we are up to. So I'm gonna make it green. So we have x minus x naught divided by t equals to v plus v initial divided by 2, right? So from that part, okay, v equals to v initial plus at. So I'm gonna write this in terms of v initial. V initial equals to v minus at. So if I take this, x minus x initial divided by t equals to v plus v minus at divided by 2. So x minus x initial divided by t, 2v minus at divided by 2. 2 cancels out here. So x minus x initial equals to vt minus 1/2 at squared. Now we have taken care of all 5 kinematic equations. Let me rewrite them all and tell me how we can manipulate those equations, okay, during the time we need them while solving our physics problems, our kinematics problems. Okay, you cannot solve all physics problems using just this kinematics equation. Yeah. What do I do with those? All right. Let me rewrite those all. So the average velocity formula, okay, kinematic equations, missing variables. So we have x minus x naught or x initial equals to 1/2 v initial plus v times t. So in this case the acceleration is missing. So if you are trying to find acceleration, don't even think about this particular formula. So v equals to v initial plus at. So in this equation, displacement is missing, or in this case displacement would be x minus x initial, or change in x. So the third one, x minus x initial equals to v initial t plus 1/2 at squared. And this one, final velocity is missing. X minus x initial equals to v t minus 1/2 at squared. V initial is missing here. V final squared equals to v initial squared plus 2a x minus x naught. Okay, in this case the time is missing. 1, 2, 3, 4, 5. These 5 kinematic equations will help you solve most of your kinematics problem.